doctors and good evening students. I'd like to welcome you to our senior thesis project, which will be talking about structural redesign of Hoover Bridge, presented by Yasmin Hakim, Saif Nawar, Karim Rabia, Andrew Naim, and myself, Amr Khalid. I'm going to take you through our outline. First of all, our outline consists of mainly 6 points. The introduction, which contains the project description. I'll be describing the history of the project. I'll be saying why did they do the project and this kind of things. And then we're going to go to the scope of work, where my friends are going to explain what are we going to do exactly in our project. Then the project data as well, our design criteria, what are the codes that we are following, and then our methodology, and we'll finally end by stating our time schedule for our thesis project. So the real name of the Hoover Dam Bridge is Mike O'Callaghan Pitt Tillman Memorial Bridge. However, the famous name is Colorado River Bridge. The location of the bridge is between the state of Nevada and the state of Arizona. The bridge takes you from this state over to that state, and it actually decreases the travel time between the two states by 30 minutes. The total bridge length is about 1,900 feet, and the height from the river till the bridge deck is around 900 feet. The start date of the bridge construction was in January 2005, and the completion date was in October 2010. The total cost of the project outreach and the whole highway of the Hoover Dam was 240 million. However, the actual cost of the construction of the bridge itself alone is around 114 million US dollars. The type of the existing bridge is arch bridge, which is a hollow reinforced concrete section. As you can see, this is the reinforced concrete section of the existing bridge. And then the total length of the bridge itself is around 578 meters. Then the total length of the free span is 333 meters. So this is actually the distance where you can put no foundations at all. The bridge is supported on 15 piers. The distance between each pier is around 34 meters. And of course, the bridge deck is a composite trapezoidal box girder, as seen in the slide. My colleague Yasmin is going to elaborate more about the design alternatives that we are approaching.
And there were different design alternatives for the Hoover Dam Bridge. The first one is the arch bridge, in which an arch is used to support the piers, which support the deck. The main advantage of that bridge is that the load is transferred to the arch, to the ends at each end. So it's less deformation and less bending moment. However, the most disadvantage of that type of the bridge is that it's unstable during construction. So it needs another structure during construction to stay. Second alternative is a truss bridge, in which a truss arch is used instead of a concrete arch, so it's lighter in weight and less dead load. However, it needs more maintenance, so it's more expensive. The third alternative is a suspension bridge, in which two towers are used to carry a suspended cable, which carries the deck through hangers. Its main advantage is that it can span up to 2,000 meters, however, it's expensive. The last alternative is a cable-stayed bridge, in which two pylons are used to support cables which support the deck. Its main advantage is that it's faster in construction, however, it needs more maintenance. In that project, as Amr stated before, they choose the arch bridge. However, we are proposing another alternative, which is a cable-stayed bridge. We selected the cable-stayed bridge instead of an arch bridge because of mainly two reasons. The first reason is that during the construction of the Hoover Dam Arch Bridge, as you can see here in the picture, they already used a cable-stayed structure to support the arch during construction. And then after that, they demolished it. So instead of doing that, we're going to use a convenient cable-stayed structure to support the deck. The other reason is that it will be faster in construction, So instead of finishing the project in almost 5 years, it can be finished in almost 2 years. And now we are going to move to the scope of work with Sid.
And now I'm going to explain you a scope of work. First of all, we're going to design the bridge, the overland bridge, the alternative system, which is a cable state as Yasmin indicated. First thing we need to do is what we need to do by preliminary dimensioning for the bridge since new elements are introduced, such as the point. After that, we're going to start analyzing the bridge and provide complete structural analysis, which will lead us to the design stage. But however, due to the limitation of time, we will focus only on the superstructure of the bridge. We'll design the following items, which are the rack, the pylons, and the cables. What is more, we're going to design some cable connections, which are the cable pylon anchorage and cable deck anchorage. Finally, we're going to do the construction sequence analysis for the whole project. Here are our challenges. Our main challenge is to be able to design the new type of structure, which none of us has encountered before. Our second challenge is to do non-linear analysis for the cables. And the third challenge is to be able to learn the new software so that we can build the model for the bridge. And our final challenge, which is still optional, is that we want to do seismic analysis using multiple supported sections. Basically, I can provide a quick definition for what is this. For typically long-span bridges, the distance between the supports of the substructure is large. Therefore, arrival time of seismic excitations may be believed. And here are our expected learning outcomes. In band, we hopefully will learn how to design the cable stay bridges and to understand the behavior of the cable stay, and we'll be able to learn the new software. And now Karim is going to proceed with the project data and design criteria.
The project data that are available for us and will be used in the analysis and design for our project are some of the original projects drawing, including plans and elevation of the bridge, showing dimension of the bridge, such as the main span, the total span of the bridge, and the bridge width. These dimensions will be used in the redesign as the same original project. We also have the topography plans showing some contour lines of both the Nevada side and the Arizona side, and those contour elevations will be used in the placement and design of the pipe. The drawings also include some design notes showing indicating the codes used in the design and some of the design loads used for the original design. All of our analysis and design will be based on H2LRD bridge design specification, as our design should and must be satisfying the limit states for strength limit state, service limit state, fatigue limit state, and the strength limit state. The loads applied on the bridge can be divided into two main types: the permanent loads, including the dead load of the superstructure, the dead load of the wearing surfaces. The second type is the transient loads, including the life load of the vehicles, the wind load, the braking force, the temperature effect, and the pedestrian life loads. For the dead load, the values of the major structure components unit weight are assumed to be the same as the original design, such as the general reinforced concrete having a unit weight of 25 kN per meter cube, the structure steel 77 kN per meter cube, and the future wearing surfaces having a unit weight of 4 kN per meter cube. For the life load, the bridge will be divided into some design lanes, and the H2 standard HL93 truck will be used in 3 different placements with the distributed design lane loads, as shown in the picture. The wind load will be applied in accordance with the H2 section 3.8.112 with a 100 years return period based on an hour velocity of 98 miles per hour. The seismic load, as Sif mentioned, we have two options: either applying it as a response spectrum or applying as a multiple support excitation. For the response spectrum, we have an acceleration coefficient of 0.2 g, as shown in the graph. And now Andrew will be presenting our methodology and time plan.
Okay. Let me introduce you to our methodology to which we're going to apply it all over the project. first of all, the software programs we're going to use, we're mainly using CSI bridges for the complete analysis and design of the project, of the model that we're going to build according to our preliminary design dimensions. And most important is that we're going to use the Midas level mainly for our analysis of the construction sequence, and also SAB and AutoCAD for the drawings. As Karim mentioned before, all our design is according to the H2 LRFT bridges design code. We choose this code because we hope to learn to get some knowledge about other codes that we don't have so much knowledge about, and also that's the code that the U.S. Department is accepting bridges in the U.S. Accepted design of bridges in the U.S. Although that we used a huge content of reference before in the initial stage of our project, but mainly our main reference is summarized in these 4 books, which is Design Flyway Bridges by Barker and Bucket, Cable Supported Bridges by Jimsing and Georgiakis, Construction Design of Cable Stayed Bridges by Scalzi, and Cable Stayed Bridges by Kirioski. And finally, our time plan. Of course, that's not according to the current circumstances, but we spent at the beginning of the semester, after our topic selection, we spent like 1 week for complete studying and researching. That's gonna extend for us for the whole semester as long as it takes. And then we started preliminary dimensioning, the cable, deck, violin, and all the dimensions for the project. It took us around 2 weeks, and then hopefully we're gonna start modeling for 3 consecutive weeks, and then we're gonna start the design procedure in 2 weeks for the 3 elements as Saif discussed before: the cable, the pylon, and the deck. And finally, we're gonna start our construction sequence analysis in 2 weeks, and producing drawings is all over the process, but calculation sheets and final report will be at the end of the semester. Here's our reference, the project. Thank you so much for listening, and we're so glad to welcome any questions from your side.